Hi everyone, my name is Pranav Sagar and I want to welcome you to the episode number 226 of Under the Microscope. Today we have with us Elisa Riedo, who is a professor in the Department of Chemical Engineering at the New York University. In this episode, we cover Elisa's research on the nanoscale materials. She also explains her pioneering work in thermal scanning probe lithography, which allows the creation of nanoscale 3D structures using a magic pen. Magic in quotation marks. Elisa also talks to us about the history and the journey of developing the NanoFrazor technology together with the company Heidelberg Instruments and its applications in fabricating nanostructures for a variety of applications, including medical and electronic devices. In the conversation, we also go into her career path, what her parents think about her being a professor now, coming from a very small village in Italy. So there is a lot to unpack here. So sit back and enjoy today's episode number 226 of Under the Microscope. Before we dive into today's episode, I would like to take a moment to acknowledge the support of Heidelberg Instruments for making this episode possible. Heidelberg Instruments is a leading force in high-precision laser lithography systems, maskless aligners, and nanofabrication tools. Heidelberg Instrument has pioneered advanced tools like the NanoFrazor, which uses the thermal scanning probe lithography technique to directly write 3D nanoscale structures with unmatched precision. Imagine precision at a nanoscale. How cool is that? And for more details, I'm going to put the links to the NanoFrazor, to Heidelberg Instruments in the description and the podcast notes. So do check that out. And for now, let's dive into the research and career journey of Elisa Riedo. Hi, Elisa.
Good morning. Hi. Thank you for having me today.
Very nice to have you. And I'm really excited to dive into your research, about your career journey, and learn more about your life as a scientist. So let's start by understanding your research. Could you please explain your research to us in super simple words?
So first of all, I'm an experimentalist, meaning I do research with real experiments and real materials and not using computers. And our research is focused on nanoscale materials. We are interested in studying the mechanical properties of these materials, the electrical properties, and also to use some of these materials to build bigger structure and then to use these materials for different applications. For example, for medical devices or for electronic devices. So for a lot of uses in our everyday life.
Okay, so you work with nanoscale materials and you're an experimentalist. So what kind of materials are we talking about here?
Yes, very different type of materials. One example is graphene. We have the graphene is, I know in your podcast you had other people talking about graphene, is a single atomic layer of carbon. We also build polymers, and also the polymers can have a very small structure, again, nanoscale structure, and can be used, for example, for some sensor application, for some medical devices. So it's really a very large type of array of materials, from carbon to metals to polymers, different types.
Do you have a favorite material? I always like to ask that because I myself am a material scientist. So of course, my master's and my PhD work was with graphene, so I have to say graphene. But do you have a favorite material? Or let's say, what is your favorite material today, as of right now?
As of right now. Yeah, so graphene is definitely in the top 10. It's a very fascinating material from a different perspective, different point of view, and I keep studying it because there are always new exciting properties that are coming out. My lab is particularly interested in actually the mechanical properties of graphene.
Mm-hmm.
So most labs study the electronic properties. We study more the mechanical properties. For example, we have recently discovered that if you take 2 layers of graphene and you apply the pressure one on top of the other one, you can transform the 2 atomic layers in a single layer of diamond. And this single layer diamond actually is harder and stronger than a bulk diamond. So this means that you can, for example, create a bulletproof vest or armor, use it as a coating, because under pressure, when your coating is hit by the bullet or an impact of something, it becomes very hard diamond. And so these properties are extremely new and interesting to understand, also from a very fundamental point of view, how this transition happened. Because it also goes back to graphene. So it's very interesting. It's a reversible transition. So like you push down and then you release. So it's a very interesting transition. And we discovered this. So this was an example of research that we do.
That is so cool. That is so cool. Okay, tell me a bit more about the other materials.
So the other materials are materials that we build. So instead of using like graphene material that already exists or that you grow with different techniques, there is also a way to actually fabricate the material with the dimension that you want.
Okay.
So say, for example, you take a polymer, for example, right? We developed a method, we in collaboration with other groups like IBM. So this was something that started many, many years ago, yes, in 2007,
Wow.
when I was at Georgia Tech,
Uh-huh.
because I was professor at Georgia Tech for 13 years. So when I was there, my group, in collaboration with IBM, developed a method which is called the thermal scanning probe lithography.
Mm-hmm.
Imagine a pen, and imagine that you can heat this pen, make the tip of this pen very hot, okay?
Mm-hmm.
And then you have a polymer, right? And you can mold this polymer. You can, for example, evaporate this polymer where you want, or you can mold it in different way so that you use your pen like a scalp. So like you have a piece of marble and you scalp your piece of marble to create, for example, a sculpture that you want, right?
Mm-hmm.
A 3D sculpture.
Mm-hmm.
So in the same way, you can do it with almost atomic scale precision. So with very high precision, you can have your hot pen, and so you can write with this hot pen and create on the surface of your polymer whatever 3D structure that you want. Not only that, you can actually also change the chemistry of your structure. And for example, you can attach to where you want proteins, DNA, so that your surface becomes also like a mimicking the tissue. So, for example, we reproduce the bone structure. So we took a piece of bone, we look how the bone looks like at the molecular scale, and then with the nanopen, we reproduce the one-to-one image of the bone in a polymer.
Oh, wow. Oh, wow. If you would have told me that you can just do it with the hot pen, even in 2D, like X and Y dimension, even that would have blown my mind. And now you're telling me that you can use this pen to sculpt 3D structures in yet at a nanoscale with atomic precision. Wow. Okay. Okay. I have many questions. What is this magic pen? Tell me about this magic pen. Can I have this magic pen?
Yes, you actually today this is a commercial technology, so you can actually buy your magic pen, and it's called the NanoFrazor. This is an instrument sold by a company, and the NanoFrazor, we actually have one NanoFrazor in my lab at NYU in New York, and we use it right now. Actually, we have a very exciting project.
Okay, and what is this magic pen made of?
It is silicon. The microchip in the phone, they are all made of silicon. So it's made of silicon and is as a form of a cone. At the very end, it's about 5 nanometer.
So we can think of
radius.
So we can think of for people who are listening and not watching on YouTube, it's like you can imagine an ice cream waffle cone, and at the tip of the waffle cone, you have the radius there. Sorry, go on. The radius at the tip is?
About 5 nanometer.
Okay. Okay.
So that's why you can write with very high resolution. It's very small.
So it sounds very much like atomic force microscopy, right? Because there are also these cantilevers and these tips where you can do multitude of different things. I also remember that these AFM tips, it was a good month or a good week if the tip of the AFM was not broken during my research time. So how robust is this NanoFrazor, as you said? NanoFrazor is the name of the pen or
of the machine, of the instrument, of the whole instrument. So the whole instrument is called the NanoFrazor because it's
the NanoFrazor, yeah.
It's the NanoFrazor.
Right. So do we have to buy like multiple tips like we had to do for AFM?
Yes.
Okay.
Yes. So the NanoFrazor actually is, in fact, when we started in my lab at Georgia Tech, was an atomic force microscope, an AFM. That's how we started. We started with an AFM and with these special cantilevers that you can heat. In fact, the technology of the heated tip was developed at IBM. And at the time, if you want a little bit of history here, my lab was really focused on atomic force microscopy. So all my research was focused on using atomic force microscopy to study surfaces, nanoscale friction, and other type of things. So at Georgia Tech, at the same time I was hired, also somebody else was hired, Professor Bill King, and he came from a postdoc at IBM Zurich, where he worked on this type of hot cantilevers. So at the time, the idea was to use these hot cantilevers for memory application. So to use the heat to melt the polymer, like when in contact, you melt locally or you don't melt. And these are memory 0, 1, 0, 1 signal from, if you make a hole, is 1, not hole, 0, and so on. And this was called the millipede project, like the animal. The millipede, because it had many different pen. And IBM worked for many years on this project. However, at some point, they had to abandon the project because there were other memories that came on the market. And these are the memories that we all know are today available. So they were cheaper and better. So this project was abandoned. So Bill King did a postdoc there. He became a professor and he was worried, like, oh, okay, so I don't know what I can actually do with now that this project was shut down. And he was a little bit worried because main project at IBM was shut down for memory. So he came to me because I was an expert in AFM and said, I have this wonderful technology where you can heat the cantilever, but I'm not sure how it can be used for different types of applications. And so with my postdoc at the time, Robert Joskiewicz, who is now a professor in Poland, we thought about, okay, what could we do with this? And by thinking and reading, and then it was little by little emerged the idea that we could do lithography, that this pen could be used not just for memory, right, but to really build and making structure on the surface, building devices, because nanoscale devices, even microchip, the microchip that we have in our computer, phone, and everything, the size of the field effect transistor are a few nanometers. So in order to build all these little devices, you need nanofabrication methods. So there has been a lot of effort in the scientific community to develop new nanofabrication methods. And so we thought, what about we use now this nanopen as a new tool to fabricate materials, to do lithography at the nanoscale, and to change the chemistry also of the materials. Like you can heat in a metal, for example, and transform the metal in an oxide. So you can then fabricate oxide structure on the material. Or you can use it for medical devices, where you can actually change the surface of a particular polymer and make this polymer reacting with DNA or with proteins. And so you can create, for example, an array of dots. And in each dot, you can put a DNA molecule or a protein or an enzyme for lab on a chip application or other application like that. So that's how it started. And then IBM came back and worked with us. And so then the whole field of thermal scanning probe lithography really, I think, emerged essentially.
So the NanoFrazor that you mentioned, this is using the thermal lithography technology where you can make these 3D structures. You can chemically or even physically, if you're placing the DNA, probably.
Both. Yes, you can do a lot of things. It's really a very versatile technology because you can change the topography of your structure. So imagine you have a planar surface and all of a sudden you have a zigzag or a well inside the surface. But you can change the chemistry. You can make the metal part becoming an oxide. You can do the opposite. You can reduce an oxide back to a metal. You can crystallize. You may have a sol gel and you can locally crystallize and create crystalline structure. You can use chemistry and then change the local chemistry. This is something that my lab has really worked a lot and still working on it, where we have a polymer. This polymer is done in a way that you can locally, by heat, activate a chemical reaction at the nanoscale. And this chemical reaction makes the polymer becoming like a glue for certain chemical biomolecules. And once you create that small glue pieces on the surface, you take your sample, you dip in a solution with the biomolecule that you want, say a certain protein or say an antibody, for example. So this is something we are working right now. You can put it with a certain antibody, for example, COVID, then the antibody attach only where you have put the glue. And then all of a sudden you have on the surface a pocket of antibodies for the COVID in the position that you want. And so you can create biosensors with that. Because you can have, for example, a field effect transistor underneath your pocket of COVID, and then use the field effect transistor to detect the presence of COVID in the solution. So you can use it, for example, for rapid test for detection of viruses or bacteria.
Is it safe to say that this thermal lithography technique and also with the NanoFrazor, basically any sort of experimental scientist where you need fabrication and precision and site-controlled experiments in the field of chemistry or physics or like photonics, even biotech,
Yes.
pharmaceutical, basically this thermal lithography technique can be used, not just natural sciences, but life sciences as well.
That's correct.
Wow.
That's correct. So you can use it to build electronic devices. For example, we have demonstrated that field effect transistors built with the NanoFrazor, with thermal lithography, instead of using conventional fabrication techniques like e-beam lithography. Now, e-beam lithography is a conventional fabrication method that you find in clean room all around the world, and in companies as well, in semiconductor companies. So instead of using that technique, you can use the NanoFrazor, the thermal lithography technique, and the result are field effect transistor based on 2D materials like graphene or transition metal dechalcogenide that are way better than the others built with more conventional methods. And it's much simpler. Like you don't need ultra high vacuum. So this is something you can have in your own house almost. You don't even, no, but it's interesting to me, right?
Yeah.
You don't need high power, for example. So you don't require like a high power outlet. You can plug it in like your oven. And then you have it in your living room, and you can build a transistor with that.
Why not? Why not? That is actually true because the power, the amount of chemicals, the time, basically all the resources that go into the fabrication, and then the time and the chemical, like everything is just, this is just more efficient and more, let's say, greener for fabrication.
Greener, definitely more sustainable, because the other methods require vacuum, ultra high vacuum sometimes. So that per se is a lot of energy waste to create the vacuum. Then you have the high energy electrons. Again, we are talking about kilo electron volt, high energy. So it's definitely a more sustainable nanofabrication method.
And everyone should be using it for sure. I visit labs quite often when I'm giving talks at different places, and I wouldn't be surprised if I just see that the NanoFrazors are just popping up everywhere. I won't be surprised because I feel like this is something that every lab should or could use.
Yeah, in some sense, it is happening, right? Because so the company that started the production of the NanoFrazor was a spin-off from IBM. So it was a postdoc working at IBM who decided to start a startup. Felix, so I know him very well, of course, because we were all working together. The beginning was hard, as always with a startup, right? So our NanoFrazor in my lab was the first one in the United States.
Oh, wow.
Nobody had one, so we got the first one in the United States. But now the NanoFrazor, a lot of clean room have it at MIT, Harvard, and nanofabrication. They have one in Europe. There are many everywhere, also in Italy. I'm Italian.
Okay. That's brilliant. That is brilliant. I'm very happy to hear that. And thank you also for taking the time to tell us about the history of the technology, because that is always interesting, like how these discoveries or these now commercially available products, for example, how they come about. I always find it really fascinating and beautiful. As Elisa is sharing her research, I think it's a good time to discuss how Heidelberg Instruments NanoFrazor enables some of the most cutting-edge experiments. So the NanoFrazor's working principle, thermal scanning probe lithography, uses a heated probe to locally evaporate material. allowing researchers to create 3D nanostructures with incredible accuracy. Beyond that, the NanoFrazor also allows mix and match of lithography with their integrated direct laser sublimation module, giving researchers even more flexibility for complex designs. Additionally, with the new parallelization module, they have introduced the decapitated cantilever arrays, which allow writing with 10 tips. 10, not one, not two, 10. 10 tips in parallel, which dramatically increases the throughput. These innovations are enabling researchers to push the limits of what's possible in the fields like quantum devices and biomedical application. I'm going to put the link to NanoFrazor and more information about these technologies in the show notes and in the description, so do check it out. All right, let's get back into today's episode 226 with Elisa Riedo, a professor at the New York University. Speaking of Italy, let's get into a bit of your career journey, right? So I'm sure a 10-year-old Elisa in Italy was not thinking that she will have the first NanoFrazor in the US, or she would be working with IBM and creating this wonderful magic hot pen. Can you tell us a bit about your career journey so far, a professor at the New York University?
Actually, my idea about becoming a scientist started quite early in my life, probably around 10 years old.
Wow.
Yes, I know it's a little bit strange, also because nobody in my family was a scientist. So I come from a household where my mom was a stay-home mom, and my father was working as an interior designer and not even have a diploma at the university, right? Nobody has a degree at the university in my family. I come from a small town outside Milano. And in this, actually, I come from outside a town outside. So my elementary school was really tiny, and my family did never talk about science or nothing. But for some incredible reason, I ended up with a book. I think it was like a church fair. And the book was about Albert Einstein. There were letters of Albert Einstein written during World War II. And I felt that these letters were so inspiring. And I think they opened a new world to me. Coming from the countryside, very simple life. And all of a sudden, I'm like, wow, there is a world there that I don't know. And I thought, I want to be there because it felt so interesting. They were letters. So he was talking about his life, what was happening, and his approach to science, to humanity, philosophy, music. And so I bought a second book about Albert Einstein. I didn't understand anything because it was talking about the photoelectric effect and the special relativity, but even more felt like, oh gosh, this is so amazing. The mass that can become energy. Like this idea and the time that is contracted, the length that are dilated. And so I started to mature this idea of becoming a scientist and travel to United States because that was the point. Go to United States, maybe to New York because I loved big cities. So I had this dream to go to New York City and to explore the world. And that's how I started. And since then, it has been like a constant dream. It was more a dream without really knowing where I was going. I think that may be what characterized my life in the sense that it's not that I thought, okay, I want to work, I don't know, like you said, on nanomaterials. It was more like, I want to be part of this community of people who travel, who sit and think about science, make an impact on the world, but I didn't know how. So I just went. I went to the university, I studied physics. I had a lot of crises in between. It's important to say that because I think that it's important to realize that life, scientific, above all, life is never a straight line. So many times I felt like I have to quit. This is not what I want. I'm not good enough. I'm not motivated enough. A lot of right bumps on the way, but I carry on. I continued, and I married a physicist. Maybe that's part of the problem. So I went to the University of Milano. I studied physics. Then I started my PhD. Then I met my husband. Then I wanted to quit because I went away from Italy. So I felt that I was homesick. So I wanted to go back to Italy, but my husband wanted to go to United States. So we said, okay, I say 2 years, no more than 2 years, then we go back. We never went back.
That's quite.
Yeah, I don't know if that was too much or too little, but I tried to summarize.
No, that is perfect because I want to hear the stories which are not written in your Wikipedia page or on your university page or on your website, because the CV anyone can get, like your resume that, okay, I was at Georgia Tech, I was at Polyme, I was at but I want to know the real journey, like the sides that are not covered usually. So what did your parents think about you, for example, studying then at Polyme, or you becoming a professor, or during your career stages, being a master's student, a PhD student, postdoc, second postdoc, professor? What did your parents say? Hey, where did this come from?
Yes, my mama always told me, certainly it's not from me. She always said, certainly you didn't get it from me, because my mom is really, she tells me that she hates math. Geometry, she never understood geometry. Physics, I think, doesn't even know what physics is, right? She never studied physics. She loves books, literature, but she's not a scientific person at all. And I think she always very surprised, like, I have no idea where you came from. Her goal for me was to get married, find a nice emotional life, which in some sense I think was helpful. Because one thing I must say is that my parents were never pushing. They never wanted me to do, I don't know, in the gifted program or to be. Today, parents are obsessed with having the kids in the best school, in the best program, and so on. My parents were like, my mom was definitely like, just focus on boyfriends. And that's it. The idea of me doing a PhD, I don't think she even knew what a PhD was.
Oh, wow.
So she didn't care less. My father, a little bit more. My father, I think, was proud of everything, but never really pushy. He always say, do what you like. Do something that makes you free also. That was also something here, strange advice, I think, but interesting. Can say, do something that makes you free. Because if you like what you do and you're free, you will be happy, which turns out to be true, actually.
Yeah. Oh, wow.
Yeah.
That is so interesting. And you made a very good point there that nowadays parents are really putting a lot of pressure on themselves and their kids as well. Like, oh, you go to this sports club, and then you go to this dance lesson, and then you do this. You have to do everything. And that basically is then restricting, or rather backfiring in some cases, where the kid is like, you know what? I'm not going to do anything. You are, I would say, a natural scientist. You were born to be a scientist. I mean, the literature, as you mentioned, right? Your mom was more into literature, and you did mention that your first fascination, let's say, of science or the world of science was through the book of Einstein.
Yes.
So, in a way, intentionally, unintentionally aligned.
Yeah, you're right. You're right. That's an interesting point because I think my mom was trying to convince me to read certain books that I didn't enjoy, more about adventure type of books. I never really liked those type of books.
Okay.
So when I got this and I felt that I like it, it was also for me, like you say, I was happy because my mom was always telling me, why don't you read more? And I didn't like it too much. So yeah,
It all makes sense now.
It is linked. Okay, we found the connection.
It all makes sense now. We have analyzed and no, but this is really cool. This is really cool. Elisa, you already spoke about a lot of research projects, the super interesting research projects, of course. If you have to pick one research project that you're most proud of, or the most fun or quirky one, could you pick one research project? I know it is difficult, so don't hate me, but pick one project and explain it to us in simple words in the section we call In Other Words.
In other words, certainly the thermal lithography is one of the things that I'm most proud of because it was something that came from an idea and now is something that a lot of people are using. So that gives me a lot of pride, right? Because it's not just something you did in your lab and then it's just one more paper, but it's something really that has an impact and it's helping other people to do more research. And also because I will talk about project that we are doing now because I'm very excited about this. So right now I say something a little bit, but let me go more into the details of this. Essentially, we came up with the idea of saying, considering that we have now this technology that we can, with nanoscale precision, activate a polymer, a surface where we want and attach, for example, the antibodies that we want, what about we couple this technology with a microchip? So a microchip, like the one you have in your phone, has millions of field effect transistors.
Correct.
Each FET is essentially like a neuron, right, in your brain. So each FET is a neuron in the brain and can deliver different signals. So our idea was, what if each of these FET can become a sensor for a different biomarker or for a different virus? So what we have done, we have built a device where each FET has been functionalized with a different biomolecule in order to be sensitive to a different virus. And then what you have is a platform that has 1 centimeter square. It's compatible with your phone and can be used to detect, for example, in your saliva, urine, or blood, the presence of multiple pathogen or multiple biomarkers. And of course, this is at the beginning, right? But the vision is to have a platform that can have thousands of detection and can be done at home, the privacy of your home. And then you can connect with your phone and have your phone maybe using AI for analysis and have a full
Profile.
screen, a full panel of your health. It can be used also through telemedicine, can be used for different type of application. And in fact, me and my collaborator, Professor Davul Sherjedi at NYU, we founded a startup. I'm now a founder as well of a new startup called, can I say the name of the startup?
Yes, please go for it. Yeah, plug away.
It's called Glaucus Technology. So Glaucus is a god is the god of the fishermen. Glaus is the god of the fishermen because we feel that our transistor are fishing, each of them, they're fishing the different virus or bacteria or biomarkers that they need to fish. So that's why we call it Glaucus. And so now we are working to develop this technology with actually a particular application to sexually transmitted infection, STI, which are actually the CDC has declared public health emergency today in the United States, and the World Health Organization also is aware of this pandemic. It's actually called a pandemic. Having at-home tests for the STIs affordable that everybody, also teenagers, can use would be really, I think, something very important.
That is brilliant. I can imagine why you picked this as a project. And also, thank you for telling us about your startup as well. And the possibilities also with this technology are endless. If I understand you correctly, it would be like smaller than even your Apple Watch display, that kind of a size, which you can have at home, and you can just test your saliva or any sort of bodily fluids or anything, basically, depending on what this particular strip is for, like a pregnancy test, but not really pregnancy test.
It's like, that's correct. Exactly. It's like the pregnancy test, except that it would be not just for one thing, but would be for
everything.
Multiple, for example, STIs or urinary tract infection, to things that are really not available today, but would make our life much easier and healthier, right?
Yeah. For sure.
Also, for example, chlamydia. Chlamydia can cause infertility, but does not really have big symptoms, so it goes undetected in young women. So 1 in 20 young women in the United States have chlamydia and they don't know it.
Wow.
Imagine, right? If you could have something very easy to test, you can test and then you get antibiotics and it's easily cured. But if you don't know it, it goes undetected, and then maybe you are 30 and you want to have children and you can't because you had chlamydia.
And you just didn't know about it, yeah.
And you just didn't know. Today, the society has changed. I think that there is really a need for that. But that is just one application, like you say. So it could be used for multiple things, but as a startup, and even as a research group, we have to focus on things because we can't do everything.
Yeah.
It's very challenging. Even the fact that it will work, it started to work, right? We have a paper just accepted now, but it will take time before the full technology will be
ready.
A product.
Oh, but that's really cool. This is really cool. And it will also take the burden of the healthcare system, right? It will just make everyone's life easier, because now if you want to get your blood tested or your any sort of test done, you have to make an appointment with your general doctor or with the pathology lab. You have to go there, you have to do the test, and then it takes a few weeks. And then you oftentimes are like, yeah, okay, I don't have time for this. I just postpone it. It's not really bothering me so much. But if you have something that you can use for a quick test at home, that would be brilliant. And then the sense of urgency to some extent that, okay, I have to prioritize this.
To go.
Yeah.
Yes.
Yeah. But this is brilliant. This is really cool. I hope, and I know it sounds easy that, why don't you just do it for the chlamydia? Why don't you just do it for this, like all kinds of different things? But it takes a lot of time and effort to test this and to create this test or the product. So you have to focus on one, the epidemic which we are living in right now, let's say STI or chlamydia. So you have to start and focus on one and then go step by step. So I look forward to buying your product just in whichever shape or form in the near future. just to make sure that everything is fine, everything is okay, just to have that. That would be brilliant if we can have that. And I'm sure we will have that because we need that. And we have brilliant scientists like you working on it. So that's going to work out.
Thank you for the trust.
Of course. It's very clear to me, right? Like also when we spoke about your research and now when we spoke about your company or your current research project that you're proud of, it's very clear to me, Elisa, that the research aspect of being a scientist is really something that keeps you in science for sure. But as a professor and now also as a founder or co-founder, what else do you like about being a scientist? What keeps you going? What keeps that fire in your belly going?
Thank you for this question. Actually, probably the thing that keeps me there more than the science is the possibility to work in a team. I'm a team player, 300%. Like for me, I would say the biggest joy comes from doing this type of studies together with others. I really enjoy that. I enjoy the excitement of, brainstorming or doing the experiment and then trying to understand. It's like an adventure. And I like to do adventures in company. I'm not good in loneliness. I know that we read a lot today about mindfulness and learn to be alone and be happy alone, but that's very hard for me.
There are no lone wolves in science. There are no lone wolves in science. It's a community.
So
thing,
it's
for
a
sure.
community, and I like with my students and postdocs and collaborators. So that's the excitement, the ambition, and then all the up and down, right? Because you think to understand something and then you don't, and then there is even publication I enjoy. Like you want to publish in Nature, and then it's always a fight because the reviewers don't want this and that, and then the editor. I have a lot of friends now in the Nature publishing journals. It's fun, I think. If you leave this as an adventure, I think it can be very exciting.
Okay, I understand. You, just to bring back what you mentioned earlier, you don't like to read about the fiction adventure, you want to live the adventure.
Now I also enjoy reading fiction because I found the fiction that I like. They didn't match the fiction of my mom. I have different tastes.
Okay.
But I do enjoy actually a lot fiction now, reading fiction.
Okay, then Mama is also happy. Phew, that's important. Okay.
Yeah, and I'm married, so she's okay.
Perfect. Tick, tick, tick. Done.
Done.
Your father said, like, be free and you will be happy, do what you love. That is also done. This is
done. Everybody's happy.
Everyone's happy. You're happy. Perfect. That is brilliant. You did share your journey and your scientific experiences and everything. And I only got the highlight reel, right, in the last 1 hour that we are speaking. Let's say today, because you also have had experience in different labs and different environments, and you are at a place in your career where you can have like a overview. So if you had 3 wishes to improve your research experience today, what would you ask for? And I'm not promising anything here, okay? 3 wishes, go.
3 wishes, okay. Less emails.
No.
The emails have been great. Technology, internet has been great. But I feel personally that it's starting to become a burden. So I would decrease emails. And maybe also Zoom. I would decrease Zoom.
Phew, good that we are not recording on Zoom.
More human interaction. I would like to increase the human interaction because after the COVID, people work more from home, which has positive effects. But I don't know. Yeah, I feel that. And the third one would be to slow down in general. Which are related, the three, if you see. Because I was even thinking, if I have to go to a meeting in person, I have to slow down because you have to close your computer maybe walk a few blocks, go in the office of your colleague. So, or even, I don't know, whatever, grocery shopping. You have to go in a grocery shop rather than doing Amazon and it comes home. So I feel that's, and so everything has become also very fast. Yeah. So I would like to slow down.
Yeah, absolutely. I think all three of your wishes, as you said, they are also combined, like they're intertwined with each other. Less emails for sure. And I can tell you that I'm in a position now because I was in corporate for 5 years. I was at Springer Nature and then I was at another company. And I'm definitely very happy that now that I'm the founder of the Science Talk, I get to call the shots and then I get to decide how many emails I write. So this is brilliant. So you're on the way to get there. But I see, like jokes aside, I see what you mean with the number of emails. And also, I think now, even now, like the emails or the messages or even the LinkedIn posts I see, they're it's very clear that person did not write that email. They use ChatGPT to make it fluffy and I'm like, can we just get to the point? Can we just like but yeah, less emails, less number of online meetings. It does make life easier. But as a scientist, I think, especially if you're an experimental scientist, there are so many things, so many discussions happen in the lab and spontaneously stuff comes out of it. So in-person interactions definitely should be prioritized. Next time when we record, maybe we can record in person.
Yes.
That would be wonderful. And also slowing down. This is something which not a lot of people tend to do because I'm too busy, I don't have time. But you have to slow down to take the full picture, to be thankful, to identify the loopholes in your grand scheme of things. It's very important. I agree.
Even for creativity, I don't think you can be creative if all you do is running, talking.
Definitely. And you do need that. Everyone needs that. And as a scientist, you definitely need to have that creative space, a time where you're not doing anything and just thinking and making sense of things. I cannot grant your three wishes, but I feel like you are more empowered to make your wishes come true than I am. Very valid wishes. And I hope you'll get less number of emails. For everyone listening or watching, try not to write Elisa emails. Just go knock on her office door and just be like, hey, we need this. And I guess she will be happy with that, more happy with that.
Yeah.
This has been wonderful, Elisa. But before I let you go, I have one last question for you. And that is about your time on our curation account on Blue Sky, which is called Under the Microscope. Is the same as the podcast. Every guest on Under the Microscope gets one entire week, Monday to Sunday. They get the keys or let's say the login credentials to the account, and then they can talk about anything under the sun. And this is a great opportunity for our followers, our community, to get to know how it is like to be, let's say in your case, the professor at the New York University. How does your day look like? What is your team? What is your lab? So what can the followers expect in the week that you are taking over our curation account?
Okay, that's a good question. My team is made of very fun PhD students and postdoc who will help me to populate that. There are people working on the NanoFrazor who will also be part of populating that content. Yeah. There will be maybe some videos about my lab, how it looks like, a little bit of speech about people in my lab, their experience, what they like, what they don't like.
That sounds great. If I could put in a request, I would love to see the 3D creations at a nanoscale. I would love to see pictures of those SEM, optical, whatsoever. It doesn't matter. I want to see that.
Optical, very hard to see. They're too small.
I know.
That's the problem. Even SEM is a little bit too hard. But what we can do, we can upload a video while we do it because the machine allows to like fabricate and image.
Oh, wow.
It has an in situ imaging as well. So you will see the writing and the imaging. So at the end, it's like a printer. When you print
like a 3D
with a printer
printer.
at home, like, so you will see, I don't know, my photo, for example. You can have my photo in 3D, for example.
Oh, wow.
Or your photo if you want. We can do your photo.
That
Let's
would be
see.
creepy.
Let me talk with or usually we have the Mona Lisa. These are we have the Mona Lisa, Feynman, this type of recognized icons.
This is really great. This is really great. It's going to be great. And thank you very much for your time, Elisa. This was wonderful. And looking forward to the posts, looking forward to speaking with you again. And next time we will be recording, hopefully in person. So thank you very much for your time. I hope this was great for you as well.
It has been great. Thank you very much. It was great and fun. And I hope that the audience will like it.
I'm sure they will. As we wrap up today's conversation with Elisa Riedo, I want to say a huge thank you to Heidelberg Instruments again for their continued support. Using the NanoFrazor's thermal scanning probe lithography, researchers can now sculpt with atomic precision. Atomic precision! How cool is that? While the mix and match lithography approach with integrated laser sublimation expands what's achievable in device fabrication. And now, with their new parallelization module, featuring the decapitated cantilever arrays that enable 10 tips to work simultaneously, the possibilities for scaling up the nanofabrication are greater than ever. Heidelberg Instruments is empowering scientists from around the world to turn groundbreaking ideas into reality. For more information on their state-of-the-art tools, please visit the website heidelberg-instruments.com and nanofrazor.com. I'm going to put the links in the show notes, in the YouTube description, so do check those out. And as always, thank you again for listening, and I will see you in the next one.